The title of the talk is a bottom-up approach to the construction of socially optimal discrete choices under congestion. This is work done in collaboration with Noureddin Toumi, who was my PhD student, together with Jérôme Leny, who's been the co-director for this research. Noureddin is about to graduate soon, hopefully. Okay, so very briefly, the content of the talk, I will start justifying the interest in discrete choice dynamic models. Then we'll formulate an optimization problem, a social optimal control problem. So you can think of it as a cooperative problem. A cooperative game. Now, it turns out we're interested really in asymptotic results, as it's a multi-agent problem, as the number of agents goes to infinity. But it turns out that contrary to our normal approach to these types of problems, where we send the number of agents directly to infinity and then work backwards towards the finite game, in this case, the sort of person-by-person schemes that we've used in the past just cannot apply, because the nature of the problem will be non-convex. So we will work bottom-up, that is, we'll start with a finite population and study the properties of the optimal control solution. And then we'll work our way from finite to infinity, and then back from infinity to finite to qualify the quality of the approximations that will result. So the last two parts will be the analysis, the 4 and 5 will be the analysis of the infinite problem. And then we'll show some simulation results and draw some conclusions. Okay, so yeah. So applications, what discrete choice theory has been very much used in a static context, and it's a theory that has led to Nobel Prizes with McFadden, and it's basically trying to analyze the reason behind which people make some discrete choices, such that do I go to work using a car or a subway? What type of city I decide in? What type of school do I send my children to, or university, and so on? These types of discrete choices. And what McFadden was able to bring out was the fact that underlying statistical data spoke a lot for the conclusions that people drew when they asked such questions. And there was some randomness, of course, in the process also. And he was able to anticipate many decisions ahead of time. For example, they were trying to build a subway, deciding whether it was worth it or not. And his analysis was able to get very close to what the people wanted. Now, here, this is dynamic discrete choice. And so there are dynamics. There are multi-agents, as in discrete choice problems. Except now the discrete choices can be a number of things. The paradigm that we will be thinking about today is evacuation, a crowd with multiple exits. But this work could be applied to micro-robots, for example, that need to be assigned to potential multiple tasks in a most effective manner. Search and rescue missions, when you have several helicopters or planes or drones that are involved, that you want to cover an area. And also one can argue that some resource allocation problems, such as in healthcare, for example, the assignment of patients to doctors in an emergency, can be viewed also as some sort of a dynamic discrete choice problem. Okay, related literature, the evacuation, the crowd models, and so on is a very active area, and in fact, mean field game theory has been applied in this area with Jehish, LaChapelle, and Orel, but none of them they're essentially they model crowding effect using nonlinear repulsion functions. And the introduction of nonlinear function makes mean field games solutions much more complex because they have to rely on PDEs. And we know that computational PDEs can, as soon as the dimension of the state space, individual state spaces increases, the PDEs become very difficult to solve. Plus the fact that we don't have an analytical handle on the solution. So really the overarching message here will be we try to cover these situations using a more restrictive linear quadratic framework. Now also team games is an area which is related, of course, to social games, excuse me, social games. So there has been some work in particular by Sanjari, for example, who studied coalitions among large numbers of agents, but a competition amongst coalitions. And then Arabnadi worked with, and co-author worked on linear quadratic team games. Then there's also the social optimization within the linear quadratic MFG framework. Now, Hongen and co-authors in 2021 has studied social linear quadratic social optimization problem when there is a common noise and was able to get some result. But there is no discrete choice involved. And really the first time that these dynamic, to the best of our knowledge, that these discrete dynamic problems have been formulated was in our group, essentially, with Salab and Jerome, myself, who is now working for Amazon in the US. And these were first Nash type non-collaborative. And then when we got to the collaborative part, things failed. I mean, we kept using the person by person concept, which is really a Nash concept. But for the social case, the restrictions were very high. And also, it was an aggregative type of game in the sense that agents wanted to remain together. Now, the situation we're studying here is one where on the contrary, because it's a congestion problem, we want to have a congestion cost. But in an LQ framework, that means actually the situation which is desirable when you have an evacuation is you'd like agents to be maximally spread in space so that they can move as quickly as possible. So there's a cost, there's going to be a deformation of the trajectories of agents relative to straight lines, because that would mean that they can go faster. So to account for that effect, we introduce a negative cost, that is a reward for spreading maximally in space. And it turns out that the reward can be reduced to the summation of agent positions relative to the mean trajectory. So that's what maximizes variance in space. So we introduced this negative cost, which is really a reward. And as a result, the the problem is no longer convex because in an LQ framework, the typical assumptions is that the Q matrix that penalizes state deviations is semi-positive definite. Here, this assumption fails now. We're going to have to deal with negative definite Q matrices. This will have this will introduce a fragility in the optimization. We also introduce a stress effect, but that's a classical, positive definite contribution, whereby the agents feel a stress as long as they are not sitting at their final destinations. And of course, we're interested in decentralizations and large-scale asymptotics. Now, as I mentioned, we won't be able to use a person-by-person optimization, which is the classical way that mean field games have worked. So, excuse me. So now let's get to the formulation of the problem. Essentially, we have multi-agents that have to choose amongst a finite number of destinations. Along the way, they're going to want to spare their energy, but at the same time, they want to stay away from the mean of the population. So the formulation will be that we have a double sort of objective in a finite population. One is finding the best agent to destination assignment, but also given an assignment to minimize find the control policy that minimizes the cost. So it's a two-level optimization. One is a continuous sort of variable. The other one is the discrete choice part. Let's look a bit more closely at the cost functions. So we have and the assumption is we have n agents distributed on a compact initially distributed in a compact portion of the agent space. And according to an underlying, they're sampled from some underlying distribution function. So it's a random distribution in space according to P0. So you sample that function. It gives you a set of positions. And this is going to be the only source of randomness in the problem. You want to minimize the average agent cost. So that's a social optimization problem. The dynamics are assumed to be linear. So we have a linear state space equation. And the cost, as we mentioned, there's a congestion cost, which is simulated as a reward. So the further you are from the mean of the other agents, the more reward you're getting. This is the source of non-convexity. This is the second term, the d lambda I. Lambda I is the choice of destination of the ith agent. And as long as you're away from your final destination, the agent feels stress, so pays a stress penalty. And there's so this term is meant to accelerate the motion towards the destination. And then you have energy cost. And what forces the agents to get ultimately to their destination, their exact destination, is the final penalty term. You have a large matrix penalty, and this penalizes the distance between the position of the agent at the end of the horizon, the time horizon, and the actual exit that they chose amongst capital D possible exits. So how do we attack this bottom-up problem? We proceed, in fact, in 3 stages. At the first stage, we consider an arbitrary assignment. lambda, summarized in a lambda n vector. The entries of lambda n are the destinations associated with each one of the agents, which are numbered from 1 to capital N. I remind you that I recall that the number of a destination is capital D. So in that first step, given an arbitrary assignment, we want to find what's the structure of the optimal control policy. Remember, the agents have to stay away from the beam. That first solution is going to give us a sort of a partial optimization of the control policy given an assignment. That gives us an intermediary cost function, which depends now on the assignments. In the next step, we analyze the assignment problem for fixed fractions of agents going to every one of the destinations. So that's, again, another constraint. And it turns out that this is going to be an optimal transport problem when we fix the fractions. So given those fractions, we want to find what's the optimal assignment. And in the last stage, we get another cost function again in that second stage, which is optimized both from the point of view, of the control policy and from the assignment point of view for a fixed set of fractions going to the different destinations. And finally, in the last stage, we treat these fractions, which live on the simplex, probability and d-dimensional simplex. We treat these fractions as parameters, and we have a parameter optimization problem. So this would lead us to the solution of the finite problem. So let's start with the first stage, which is arbitrary assignment, lambda n, and optimizing the control policy. The first thing we will do is to compactify the notation. So we write the individual equations, we concatenate them and write them as one large state equation. We also write the average cost with individuals as a large cost over the complete agent state space. And the matrices, the notation, this is standard notation for a quadratic form. The matrices Qn and Rn are essentially rewritten in a compact form in terms of these are n by little n dimensional matrices, the Qn's, because little n is the dimension of the agent space and capital N is the number of agents. So we rewrite them as using Kronecker products as functions of smaller matrices, which are little n dimensional. And d lambda n is the column vector of all the destinations assignments. So so remember, for a fixed destination assignment, so I fix this column vector, we want to compute the optimal control policy. So we hypothesize, we use an ansatz of a quadratic value function, plug in that ansatz in the Hamilton-Jacobi-Bellman associated with the augmented state system, and try to come up with the matrices which would correspond to the solution of the Hamilton-Jacobi-Bellman equation. One thing to remember, though, is because we have moved away from the standard condition of a linear quadratic problem, the Q matrix is now no longer semi-positive definite. It is actually negative definite. There's a danger that as the control horizon increases, the Riccati equation that you can see this Riccati equation at the bottom for the problem that was stated just now. That Riccati equation might exhibit a finite escape time. So there's a fragility, there's a cost that comes with this formulation, which is perhaps more tractable, but this forces the control horizon, forces limits on the control horizon, past which the problem may not have a solution. That is, the agent may decide to run away towards infinity because it's cheaper for them to do so, as they earn a reward when they escape the mean. So that's a fragility to remember. On the other hand, if you have an evacuation problem, it is normal that you would have limits on the time during which this should happen. So from the physical point of view, it's not necessarily an unnatural thing. So assuming the solution to this Riccati equation exists, it turns out it can be consolidated again in terms of what's on the diagonal and off-diagonal terms, and written in terms of much lower order matrices, which are n-dimensional, with little n being the dimension of the agents. Also, there's typically a linear term in the cost, in the value function. Well, it turns out that linear term, all agents that share the same destination in the assignment share also that this is a vector here, n-dimensional vector. And from 1 to d, the agents, all the agents share that part of that one-dimensional vector, which is that term. Alpha k's, pk's are the fractions that go to the different destinations. Alpha k's are n-dimensional vectors, again, which satisfy linear differential equations once the Riccati equation is solved. But the difference will come from that one vector. So this is common for all destinations, but this will change according to the destination. So this solution, which is written for an arbitrary assignment, turns out to suggest that agents that share a common destination somehow would share a lot of features in their controls. And then finally, you have that constant term in the quadratic expression for the cost function, which is a quadratic form in Pn. So that's the first stage, which tells us the structure of the solution of the optimal control problem when it exists. Now, under what conditions can we guarantee that the optimal control problem exists? It turns out, of course, independent of n, and independent because if you look at this Riccati equation, it has a size capital N by n. It's a very large Riccati equation. It turns out that one could focus on a much lower dimensional Riccati equation of order little n, the dimension of a single agent, and a sufficient condition for the large equation, Riccati equation, to have a solution is that the smaller Riccati equation have a solution. So if and interestingly enough, the small Riccati equation doesn't depend on capital N, doesn't depend on the number of agents. So we can find sufficient conditions that on the length of the time horizon, which will guarantee that a solution to the larger problem exists. So at least that doesn't mean that solutions cannot exist. It's not a necessary condition. is just a more restrictive assumption, but we know at least a range of times which we can characterize that will guarantee that an optimal control solution exists to the larger problem. Now, the optimal control policy derives from that, and it's going to be a linear feedback on the local state. So it's decentralized in that sense, but not quite decentralized at that stage because it depends on the mean, empirical mean of all the other agents. And there's an open loop quantity that goes here but which can be computed offline. Okay, but still it's not quite decentralized because you still need to observe the empirical mean. And the empirical mean itself satisfies a linear differential equation with phi1 and phi2n being solutions of reduced order Riccati equations. The cost function that emerges from this, remember this was the cost function, the optimization problem for an arbitrary assignment. Now, it turns out when we observe the optimal cost function resulting from the arbitrary assignment, it features the role of the fractions of agents that go to the different destinations. So the vector of pjn's, which is the fraction that goes to all destinations 1, 2, up to n, they're rational fractions at this stage, appears in most of the terms. And in fact, if we fix these fractions, it turns out the only remaining term is a term of this form in 13, which is related to, it's related to specifically to the assignment. So fixing the fractions that go to the different destinations and trying to solve the assignment problem reduces to essentially an optimal transport problem. You want to assign the agents to the different destinations with certain probabilities. You start with an initial distribution in space. You want to move with a final distribution that has these weights on the different destinations. And by minimizing, by choosing the assignment that minimizing, which is a solution of that optimal transport problem, which turns out, can be formulated as a relaxed linear programming problem, as in its contour of each formulation, you're guaranteed, in fact, that despite the relaxation, as long as the PNs are rational fractions, you're going to get each agent assigned to a single destination. So we call the solution of that minimization problem, that intermediary optimal transport problem, Cn of Pn. Okay, and we substitute this in the cost function, the optimal cost function of the previous problem, to get the optimal cost function under fixed probabilistic assignments to the destinations. So that's the second stage. So we started gradually getting cost functions that are more and more optimal. The first one was optimal only with respect to the control policy. The second cost function that we have in 12 is optimal for both the control policy, but for a fixed probabilistic assignment. And now we're going to consider the third stage, which is the optimization problem. It turns out now that if we really want to solve the finite agents problem, we have to enumerate essentially all the possible assignments, and there's a very large number of those. It's the choose n plus d d minus 1 from n plus d minus 1. So it can be a very large number. And for each one of these choices, we have to compute, well, all these terms, I think, are essentially independent of the assignment, the first line. But in the rest, we need to compute the terms that depend on the probabilistic result that corresponding to each one of the particular assignments. So what fraction goes to each one of the destination, compute the constant term in the cost, solve the linear program for Pn, and compute the social cost, and keep repeating that until you've enumerated all the solution and order the solution until you get the minimum term. And once you have the minimum term, you can compute the U star using the control policy that we referred to earlier for a fixed destination assumption. Now, clearly, this is not a very computationally attractive approach. So this drives us to try to see what happens as n increases to infinity. Shall we get simplification? Shall we get simpler control laws? That's what the next objective is. So are there any questions at this stage? If need be, we can stop. Are there any questions? Okay.
Roland?
Yes, Tamer. Yes.
Hi, good
Hi.
seeing you.
Good seeing you.
One question which
Yes.
was prompted by the Riccati equations that you had, which were equations 8 and 9. So my question is, I mean, they have finite escape, as you have also articulated. How does the finite escape time depend on n, capital N? Is it monotonic? In other words, as you increase n, would t increase? Do you have any idea?
That's a good question.
That's a question of curiosity driven by...
that's an interesting question, Tamer. Actually, we stopped thinking about 9 when we found that 8 was provided us with a sufficient condition.
Okay.
So if 8 exists, then automatically, no matter what 9 is, no matter what n is, 9 will have a solution. But of course, let's say if we worked on a specific n, the escape time, and then we move to n plus 1 or n plus 2, does it make it worse or not? That's an interesting question, I think worth investigating. But
and you don't know how sufficient it is.
No, not really. Not really. That's a good question.
Okay, that answers my question. Thanks.
Thank you, Tamer. Yes. Okay, so now we get to, where was it? So now we want to move to the n goes to infinity situation. So we work in a purely formal way. Essentially, we look at the cost function that we obtained for the finite case and just send n to infinity in the cost function. So there's no interpretation of the problem, the original problem being reformulated for an infinite number of agents. We have only the solution, the structure of the optimal solution for fixed p, actually, fixed p assignments. In 12, we send n to infinity in that expression, and we look at the limits, the limiting cost, and the kind of problem, the transport problem that results also. So in that case, C of P becomes, essentially a bona fide transport problem where you have a distribution in space and an initial continuum of agents on a compact set, and you want to assign them to move this continuum distribution to a discrete distribution. So it's a semi-discrete problem. with particular weights, and the cost depends on these beta j vectors, which appeared earlier in the finite problem analysis, except now we've sent n to infinity, so beta j's don't depend on n anymore. They depend on particular limiting differential equations. And so we can formulate this problem on in general when we deal with the limiting cost function on this complete simplex. We don't have anymore the constraint that the p vector has to be rational components. Now it's simply the complete simplex, a d-dimensional simplex. And pi's, of course, okay, will be greater or equal to 0. So that's the limiting cost function, and we will be studying the properties of that cost function as a nonlinear function. Okay, it turns out when we analyze that function, the pieces that add up in J of P, there's several pieces. There's this term here, which is a continuous integral, but in the end doesn't depend on P. There's this chi term, which depends on P. There's this linear term, which depends on P. These two terms don't depend on P. And the cost of the optimal transport problem. Well, excuse me. So it turns out by capitalizing on convexity of solutions to optimal transport problems, we can show that this will be a convex function of P. And by working really in great detail with this, this is a linear term, it's not so bad, but with this quadratic form here, by working in great detail on that quadratic form, we're able to show, at least in the diagonal case, when the A matrix is diagonal, we're able to show that it's going to result into the quadratic part of that expression will be a positive or semi-positive definite term. So in the end, the total expression can be shown actually to be one continuous and convex, which is a rather interesting property, of course, because we didn't know anything about the discrete case, but now that we went to that continuum, we can see convexity emerging, which is a very desirable property. So we can envisage using subgradient type of and projected subgradient methods to optimize that cost function. And in fact, an explicit subgradient can be computed for that cost as we move to try to optimize P. So this is concerning the properties of P. Now, what can this limiting P tell us? We look for the since this is convex, we on a bounded simplex set, we're going to be looking for following the derivative to try to come up with the optimum P star, that is the optimum distribution assignment on the different destinations. And once we have that optimum P star, this optimum P star, in fact, allows you to come up with two types of things. First, each one of the P star is associated with an optimal, with a particular partition. That optimum P star is attached to a partition of the agent space into what can be shown to be polygonal convex sets. Okay, cells. So each agent in a given cell is associated to the destination associated with that cell. So you have sort of hyperplanes subdividing the initial agent space, and which assigns any agent inside that space towards their destination. The second thing that we can learn from that is the optimal control policy, which is a local feedback. Then on the local state, it's an open loop function which depends on the optimum p stars and time, but also it depends on a function x bar. But this function x bar now, unlike the finite case where this was an empirical agent trajectory and that made the control law not quite decentralized, over here we can generate that that trajectory in a completely open loop case. So this is a truly decentralized control policy. And also there's the assignment rule, which is dictated by the particular p star we found. This dictates an algorithm, therefore, for computing potential approximate control laws to a finite agent problem. So the idea would be to compute the p star that optimizes j of p, go to the partition that goes with that particular p star, then consider the finite agent distribution. Where do the agents fall within the cells dictated by the infinite partition? Use the control policy that's attached, which I just showed, which is attached to the so-called continuum strategy, and then hope for the best. In other words, hope that whatever solutions you came up with is close enough to the finite agent problem optimal solution, which, remember, was obtained via an enumeration approach, heavily computational. Well, the main result ultimately, other than that the convexity properties and the search algorithm for the optimal p in the continuum strategy, is the epsilon optimality. So we're going to define several costs and approximate costs. First, there is the Jn of Pn, which was the cost. So if we go back to this expression, this was the optimal cost. Well, this was the optimal cost for fixed fractions going to the different destination. We can define an extension operator by embedding these rational p's into the simplex. So we define this as Jn bar of p as this extension operator, and also we define the optimal solution, the suboptimal solution obtained for the finite agent problem using the the continuum strategy that I just mentioned. So it gives you a suboptimal cost, that is with the p star. So we have these three quantities. Well, first we can prove that with probability 1, so almost surely, as the number of agents increases to infinity, this extension operator converges uniformly to the j of p, which was that equation I wrote earlier, which was purely formal limit of Jn of p. So they converge uniformly. So for any p, the speed of convergence is uniform. Secondly, one can show that as n goes to infinity, the suboptimal cost that we get using the approximate continuum strategy-based policy for the finite agents converges to the minimum of the limiting j of p. And then ultimately, using these two results and a sandwich kind of argument, we're able ultimately to show that the minimum of the essentially the minimum of the finite of the optimal policy for a specific choice of P, as P is limited to rational fractions, the distance between this and the optimal and the suboptimal n that we get by using the partition dictated by the infinite control policy, they converge to an arbitrary small number as n tends to infinity. So this is an epsilon optimal policy. So this sort of closes the analysis. We can work, this justifies working with that simplified limiting problem to solve the finite agent social assignment problem. And these are some of the numerical results we get. So for two destinations represented by a circle and a lozenge here, with initial distribution in space, if we look at the partition dictated by the continuum strategy, it is this this segment here in space. The gray circles and lozenges are the initial positions in space. Lozenges for the ones that are supposed to be going to their best choice is the lozenge destination, and the circles, the best choice is the circle destination. The blue circles represent the only deviant agents relative to the finite exact optimum solution for that problem. We have played here the same problem, but with different time horizons, which of course, the longer the time horizon, the more threatening it is for finite escape time. And you can see as the horizon increases, there's a deformation of trajectories, indicating that agents try to capitalize on the possibility of going faster by moving away from other agents in their trajectories. So when the time is too short, we're not able to capture the congestion effects, but as the time increases, within, of course, existence guaranteed bounds for the optimal control, we can see deformation of the trajectories. And again, we can see some more, the numerical behavior seems to be, so this may be, I don't know if this relates to Tamer's earlier question, but you can see that the disagreement between the assignments of the approximate policy and the exact, the number of disagreements increases slightly. And this is for fixed P's, the distance between the approximate strategy, because you could also define an approximate strategy for an arbitrary P. So if we compare the continuum cost function, which is the black thing, the red, we remember this is a probabilistic Monte Carlo kind of thing. We have a P0 distribution, we sample it, and then we have many samples, so 100 agent samples, and we repeat the experiments. We have Monte Carlo experiment, and we look at the mean costs. We can see that the blue and the red costs, the blue being what you get when you use the approximate strategy, are very close, almost uniformly. And the closeness to the limiting distribution, which is the black one, even increases as the number of agents increase. So it shows that the theory, this sort of validates our theoretical conclusions. So with that, I think I can get to my conclusion. So we introduced a new class of dynamic discrete choice models, but this time collaborative. we could not apply we could not go to a limiting analysis because normally we use person-by-person optimization to get to the finite agent situation, but that wasn't possible because of non-convexity. So the alternative was to identify the nature of the solution through a bottom-up approach, and then go to the limit, and then from the limit go back to the finite agent solution to come up with an epsilon-optimal result. This, however, has been an analysis where the only source of stochasticity were initial conditions. Now, if you start putting noise along the trajectories, it's an infinitely more complicated problem because agents could be tossed around as they go along their paths, and they may change their mind as to what the optimum exit could be. You know, this is substance for future work. Well, with that, thank you very much for listening.